Last week, we spent a lot of time talking about acute injuries and overuse injuries and how to think about those from a mechanical loading perspective. So acute injuries are pretty straightforward, right? Because if you think about it from a stress strain perspective, let's say we're looking at the ACL, somebody's getting tackled from the side. The ACL, you're going to induce some change in length as a function of the applied stress, and maybe the slope of this curve is steep because the loading rate is high. But once you get out of that linear region and into the plastic region, so let's say the linear region ends here, and we're over here in the plastic region. Once the applied stress, meaning force divided by cross-sectional area, gets up into this area, now we're doing physical damage to that, in this case, ligament. And if you go all the way up here to the ultimate strength or beyond, it's just going to break. So up here, this would be like rupture. This would be like ligament strain, or when you sprain your ankle, but you don't tear anything off. You're up here in the plastic region. When you completely, say, rupture your ACL, that's up here. Now, we talked a little bit about how viscoelasticity helps ameliorate the effects of high loading rates to some degree, because in the case of high load that's applied slowly to, say, a tendon or a ligament, the stress strain curve might look like that. But if the load is applied very quickly, we get a steeper, stiffer slope. And that means that we can, in a sense, we can absorb more energy because this area is bigger than this area, using that area under the curve interpretation of the stress strain curve. So to some degree, that can help protect us. But the fact of the matter remains that if you go up beyond the end of that linear region, even for a single loading cycle, you are going to be inducing physical damage to whatever tissue it is. We also maybe emphasize that different materials will, because they have different stress strain curves, will be more or less vulnerable to acute injury. So a really well-trained athlete might have a very stiff and strong tendon, which has a stress strain curve like this. Somebody who's older or a novice, beginner, less well-trained might look like this. So it's quite obvious that this person is going to handle sudden loading much better than this person. So this is the mechanical interpretation of acute injuries, which is relatively straightforward. Where things get a little more complicated is with overuse injuries, where when we have exposure to loading that does not go all the way up until the material breaks, but just goes up and down and up and down and up and down and up and down over and over and over and over again, right? Running, sprinting, plyometrics training, jumping, this kind of thing. That can induce small amounts of microscopic damage that accumulate more slowly. And we introduce the idea of this SN curve to start to build up an understanding of how repeated exposure to loading damages material. And we talked about how you might do an experiment to get a curve like this by taking a bunch of samples of, say, tendons from animals or from cadavers and loading them over and over and over at different levels of maximum stress. So maybe one of them you load it like this much and then relax, and then this much, and over and over and over again. And you just do that until it breaks. And then a different one, you load it more with a greater force, meaning so greater force, so same cross-sectional area, greater stress. And we saw that there's this very characteristic curve. It looks like kind of this. And I tried to emphasize that on the x-axis here, we've plotted the number of loading cycles to failure. So this, you could interpret this as steps taken, reps performed, number of plyometric jumps, that kind of thing. Each one of those is one loading cycle, right? One squat rep, that's one loading cycle. One step taken while running, one loading cycle. And then I haven't labeled stress here. Sometimes you'll see it expressed in units of megapascals, like I think on the homework it's in megapascals. That's just a unit of force divided by cross-sectional area. But I try to emphasize that on the x-axis here, we have a number of loading cycles to failure plotted on a log scale. So notice how each jump from here to here to here to here to here to here goes up by a factor of 10x, as opposed to on the y-axis, that's 25, and that's 25, and that's 25, and that's 25. So this has some very important implications for understanding the dynamics of how different loading rates, or how different amounts of loading and different repetitions, meaning number of loading cycles, affects your risk of injury. And we built up this idea that we could think about different types of exercise as existing as different points on this plot. So maybe you go for a walk with your friends, and maybe you take some modest number of steps, and the loading is really low because you're just out for a walk. Whereas maybe you go running, and you just so happen to take the same number of steps, but the loading is much bigger, so you're up here. So that is more damaging because you are closer to where this would intersect this line, which is where you'd experience injury. We also saw that even things that are very low loading repetitions, like maybe a sprinting workout, you might only take a few hundred, couple thousand steps, but the loading would be really high. The same for plyometric training. Plyometric training might only be 100 loading cycles, but if it's really aggressive box jumps, you might be way up here. And the idea is that if you get too close or on the other side of this curve, which again is it's the average number of loading cycles until failure at a given amount of stress, mechanical stress. If you end up over here, you are almost certain to be injured. So this gives us a very useful way of thinking about the mechanics of overuse injury and how our training programming would affect our risk of injury. So we might think about what happens if you double the number of loading cycles versus double the mechanical stress. So from a perspective of, let's say, here, if we double the loading cycles from 100 to 200, we only go to about here. Because remember, if you looked at like 2, 3, 4, 5, 6, 7, 800, be like 2, 3, 4, 5, 6, 7, 8, 9 here. That's good. This is going up by a factor of 10. Whereas if we double from, say, 50 to 100, we go up to here. So be careful with the log scale. That's doubling the number of loading cycles, and that is doubling the loading or the stress per loading cycle. So there's a much more dramatic effect of increasing the stress than there is from increasing the number of loading cycles. That's one of the big takeaways of interpreting SN curves. Additionally, we introduced this more sophisticated idea of consuming the fatigue life of a material, such as a bone. And the idea was as follows. Suppose you are on the track team and you do a track workout that involves, I don't know, let's make the math easy. Let's say it's 10,000 loading cycles. That would be a long track workout, but 10,000 loading cycles at maybe this amount of stress. We could think about that level of stress having some associated maximum number of loading cycles to fatigue, which looks to be about 100,000 here. So we said that the idea is that track workout consumed 10,000 out of 100,000 maximum, like this is like the maximum number of loading cycles, and you consumed 10,000 of them, so like 10%. And we said that say you go into the weight room and you do some other workout that's far fewer loading cycles, but maybe more stress per loading cycle up here. So let's say it's at 50, your maximum cycles to failure is maybe 600, and you do, well, let's say it's 500 again to make the math easy. So you do 100 loading cycles out of a maximum possible before failure of 500. That consumes another 20%. So the idea is both the when you go for the run and then you go into the weight room and lift, you got to add those together. So that whole training session has consumed, again, I just picked these numbers because they're easy to do the math with, but 30% of the total fatigue life of, say, your patellar tendon. So the idea is that you have to consider all the different things you do together. And quite often you can encounter situations where maybe you go for a long, easy run and you're way down here and you've consumed very little of your fatigue life. But you do some sprinting on the track, and because the loading is so high, that session might actually do much more damage as a percentage of the total fatigue life. So the takeaway here is make sure you don't forget about low loading cycle, high loading magnitude activities. That would be things like plyometrics, explosive lifting, sprinting, hill sprints, that kind of thing. So that was everything that we did with regards to SN curves, and they're a very powerful tool for understanding the dynamics of overuse injuries. Lastly, I should just point out the connection between acute and overuse injuries. One way of thinking about an acute injury is that it's an overuse injury that happens after one loading cycle. So we could connect, if we kind of extrapolated this curve up to maybe here, whatever that point is, whatever the intersection of this SN curve with one loading cycle to failure, we would expect that amount of stress to be more or less the same as the ultimate stress of the material, right? Because if you just go up the stress strain curve until the material breaks, you've done one loading cycle to failure. So we would expect that number, that amount of stress, to be hypothetically at least the same as that. So that's overuse injuries, acute injuries, and the connection between the two.